Okay, so the final question on the ionic bonding section is question number 3. This is a compound formed between ions of X and Z. We've got a ZX2 compound, and it's asking us a couple of questions about which groups element X and element Z originally came from. And we can look at the diagrams to work that out. If we look at X in the first instance, the easiest way to work it out is to usually look at the charge. You can see that it's a 1 minus charge. So in order to become a 1 minus substance, it's had to gain 1 electron, which means it must have had 1 space in its outer shell. And you can see that there by the presence of just 1 extra dot electron. And in order to do that, it must have been in group 7, because it's gained the 1 electron. Okay, so we just gained the 1 electron. And if we do the same for Z, we can see it's a 2 plus charge, which means it's lost 2 electrons, and it's this one here and this one here. So if it's lost those 2 electrons, it must have had 2 outer electrons, and so it must have been in group 2, because it has lost 2 outer electrons, or lost both outer electrons, because it must have been in group 2. So we've got that from dot cross diagrams, and question 3.2 is asking us to look at the pros and cons of what a dot cross diagram allows us to do. And on the grand scheme of it, they're quite good in giving you identification of ideas about what's occurred. And some ways in which they are good is that they tell you, obviously, the charge on the ion. They give you some good information, so you can see the charge on the ions. So that's all okay. You can see the electron arrangements very clearly. I mean, that is what it's ultimately designed for. You can see the electron arrangements very clear, and you can even, in certain instances, like we see with X and Z, you can see where the electrons were originally, which is always helpful. See where electrons started as, whether they started on the metal or they've ended up on the non-metal, etc. So see where electrons started and obviously finished if you've got a final diagram, as we have in this situation. And it gives you some structural ideas, and you can work out which groups certain things must have been in and things like that. And also, as we started to allude at the beginning, it's also very good because it gives you empirical formula information, which is the simplest ratio of elements of the elements in a compound. So it gives you empirical formula information. So by drawing a dot cross diagram, you can evaluate the formula of a compound, and you can do it in a diagrammatical fashion if you don't perhaps know any more information at the time. So empirical formula can be evaluated. So that's always good. Some of them are a lot more long-winded, but obviously we know at certain points you can use shortcuts such as valency and things like that. But if you're on a starting point, you can do by dot cross diagrams. Now, the problem of certain things, though, is that there's no three-dimensional representation. There's no size to these things. It's very difficult to see whether or not these things are twice as large. I mean, the X and the Z substances here are all roughly the same size because that's generally just how we draw them. The size ratios could be all completely wrong. So we don't know how big these things are. We don't know that in either atoms or ions, because ordinarily if we draw an initial diagram and a final diagram, your atom will probably be the same size as your ion, and in most cases that's not actually strictly true. And also we don't see the arrangement of the ions, because obviously we don't have three-dimensional structures here, and we know if we were looking at sodium chloride, for example, that's a cubic structure where the sodium and chlorine is surrounded by 6 other ions. We wouldn't be able to get that representation in a two-dimensional dot cross diagram.